In this lecture, I'd like to go over the basic rules for differentiation. There's really only two things for you to do in this lesson. The first thing would be to actually learn the rules. Fortunately, there's not many, so there's not that much to learn. And then the second thing is to actually do exercises. So do exercises. And this is really the important thing. You have to do exercises. So do as many exercises as you can. You really learn these rules by doing problems and doing problem over problem over problem. And I'll go over a few where I think there might be a few kind of problems that might arise when applying the rules. But essentially, it's your task to do the exercises and as many as you can. So let's quickly review the basic rules. The first one is the constant rule, a very nice rule because it says that something becomes zero, which is usually a nice thing. Not always, but often. So if you have a constant function, the constant function c here, where c can be any value, if you take the derivative of it, you get zero. And the explanation for this rule is just as easy. I mean, since the derivative measures change, or the rate of change, and the constant function never changes, so change is zero. That's it. The next rule is the linear rule. So if I take a linear function, which is the equation, it's the same as the equation for a line, ax plus b, the derivative of that is just a. And that's also clear because this is a line, a is the slope of the line, the derivative is the slope of a tangent. However, if I have a line, then the tangent at any point is just the line, so the derivative is just the slope of the line. A. Just as easy. You can also justify these rules more formally by plugging in these functions into the definition of the derivative. So you remember from last time how we defined the derivative using a limit, right, of the difference quotient. If you plug this in and take the limit and kind of observe a few rules that govern how you take limits of certain functions, then you will actually get the same result, and which will give you an algebraic verification of what we just did, more or less geometrically, intuitively. And this is actually true for all the rules that we'll be encountering here. They can all be verified in a formal algebraic way using the limit definition of the derivative. And we will take a look at that in the next lesson when we try to do the whole thing more formally. In this lesson, we'll just look at the rules and how we apply them. So we'll get back to that. So the next rule is the power rule. And as the name says, it's actually a pretty powerful rule. So of course the name comes from the fact that we're looking at power functions. But this rule here is so useful. I mean, this is, if you're only able to remember three things or so, should definitely be one of the things you remember. So if you take the derivative of a power function, where important that the variable is in the base, not in the exponent. We'll get to that later. And the exponent is any number a. The derivative of that is you multiply by the exponent and get x to with a new exponent, and the new exponent is just the original exponent minus 1. So let me stress again that this can be any real number, right? So any, not just a number 1, 2, 3, so a natural number. It can be any real number. And that makes this rule so important and so helpful. Right? So on the previous slide, we saw basic rules for actual types of functions: constant, linear, and power function. So now the rules on this slide will be about functions that are combinations of other functions. So this will tell us how the derivative behaves when I take functions and combine them to build new functions. One way to build new functions from old functions is to take sums, right? And the derivative behaves really well and really nicely with respect to taking sums, because the derivative of a sum of two functions, f and g, so I drop the f of x and f of g of x here just to improve readability. So this derivative of the sum of f and g, f plus g, is just the sum of the derivatives. Very nice. And you could do the same thing just for differences. So I could say d dx, f minus g is f prime minus g prime. Right. So we have difference. But it's really only, it's the same rule, right? There's really only one rule. You can infer the difference rule from using the sum rule plus another rule that we'll see next, namely the constant multiple rule. The constant multiple rule says if I multiply a given function f, right, by a constant, then the derivative of this new function is just taking the constant and multiplying it with the derivative of f. So multiplying by constants is also a very nice operation with respect to the derivative, in the sense that it does not affect the derivative much, right? So here we multiply by a constant, we multiply by the same constant, and just take the derivative of the original function. Very nice. And these basic rules from the previous slide and this slide together already take us a long way to differentiating many functions that we encounter. So probably the most important thing that we can take derivatives of now are polynomials. So let's say we want to find the derivative of this polynomial here, right? 4x to the third minus 2x squared plus x plus 11. Right? So the rules tell us, well, how we can actually compute this derivative. So what we could do first is, well, we see that this is a sum or difference combination of many kind of smaller functions or individual functions, right? Namely this function minus this function plus this function plus this function. Right? And the product, the sum or difference rule tells us that this is the same as just taking the derivatives of the individual functions involved here and just summing them up or taking differences accordingly. So this would be d dx 4x to the third minus d dx 2x squared plus d dx x plus d dx 11. So what we used in this step here, right, this equality is justified by the sum and the difference rule, right, applied several times. Okay, so next step, now can we apply rules to compute the derivatives of each of those individual functions here? And there we see, well, this is, what does this function look like? Well, it's a constant multiple times a power function, right? So x to the third is a power function. 4 is just a constant multiple, right? So the constant multiple rule says, well, if I multiply a function by a constant, I just take the derivative of the function that I multiply the constant with and keep the constant. So let's do that. So this would be d dx, and now I multiply 4 and just have to do x to the third. Now same thing here. We have a 2, so minus 2 times d over dx, x squared. Here we don't even have a constant multiple for the next one, so that would just be d dx of x. And then we have d dx plus 11, right, which is just a constant function, right? And now I can completely resolve everything by just applying in the next step the power rule or the linear function rule. The linear function rule is, again, I would say just a special case. You can consider this of the power rule and the sum rule. And here we have a constant function. So we can now evaluate actually all derivatives involved here. So this would be 4 times, and now I would use the power rule, so I have to multiply by the original exponent and then take x to the 1 minus the original exponent minus 1, so in our case 2, minus 2 times, I'll carry over the constant, derivative of x squared. X squared is a power, so I have to take the exponent and then subtract 1 from the exponent, which leaves me with x, and then plus derivative of x, right? So you could use either the power rule or the linear function rule. In this case, you come to the same result, that it's 1, and then we're left with this one, but that's a constant function, and we know by the constant rule that's 0, so let me write here 0. But of course summing 0 doesn't change anything, so often this is just left out. But I'll put it into this step to illustrate where this term goes here, so it results in just adding 0. So I can now sum this all up, and I get 12x squared minus 4x plus 1. So to sum up, taking derivatives of polynomials, right, is just what you do is you go over them term by term, preserve the signs here, right? The last term, the constant term, will always result in 0, so the new derivative will again be a polynomial. However, since you apply the power rule, right, it will be of degree 1 less than the previous polynomial you started with. Right? Okay, that's essentially it. And we're going to do a couple of exercises from the book now to practice these rules, right? So the product rule, the constant multiple rule, and so on for other functions. So let's look at number 28 from chapter section 3.1. So this function is a little bit more complicated than a polynomial because we have all these things now in the denominator, right? So it's not a polynomial anymore because we have exponents that are not natural numbers, right? So he is a natural number, but he is not a natural number anymore. But the way to differentiate these kinds of functions is just the same, right? It might look a little intimidating at first sight because we have this, we divide by square root of t. That looks dangerous, right? But it's not really that different because the power rule, as I said before, is so universal. It applies to any kind of exponent, right? And in particular, the exponents that are come attached to these kind of functions. So when you see a term like this, if you see a function like this, the first thing you do, what I always do at least, is you might not have to do it, but I always tend to mess this up if I don't do it, is to rewrite this function as a combination of power functions so that it's clearly seen what the exponents are, and then it's much easier to apply the power rule. And to do this, you have to remember two things. The first thing is that taking square roots is the same as taking t to the exponent 1/2. The second thing is that 1 over t to the something, right, like here 1 over t squared, is the same as taking t to the power -2, right? And since here we have a combination of both things, so we have 1 over or 12 over square root of t, that's the same as 12 times t to the power -1/2. So that's what I did here. I just rewrote the whole thing, right, the whole function, as a sum or difference of certain power functions times a constant multiple. And now it's actually much easier to compute the derivative because we now can go through it applying the product, the sum or difference rule, right? We can go through it term by term and compute the derivative. So this is what I did here in this step, right? So we want the derivative of this function, and we now go through it term by term. Again, we have constant multiple 3, just carry this over. Now we just have to take the derivative of t squared, which by the power rule is 2t, right? So 2 minus 1 is just 1, and I didn't write the exponent 1 here. But that's the only case when I drop this exponent. Then next term is 12t to the -1/2. You take 12 as just a constant multiple, carry it over. Now you write -1/2. That's the original exponent, and I strongly encourage you to write this out in detail when you do the first kind of first go through each term individually first, right? So -1/2 t original exponent -1/2 -1. Same thing here. By the difference rule we carry the minus. Now we have to take the original exponent -2, right? T to the -2 original exponent -1, right? So that's our derivative, right? And essentially we're done now. Of course, we want to bring the whole thing into a nicer form. So this is what I did in this step. So I just simplified the expression a bit. So here 3 times 2 times t becomes 6t, 12 times -1/2 becomes -6, and then t with a new exponent -1/2 -1 becomes -3 over 2. Here we have minus times -2 is a +2 times t to the -2 -1 is -3. So if you want, so this is a perfectly good expression, but if you want, you can now rewrite this also as 6t minus 6 times 1 over t to the 3 over 2 plus 2 times 1 over t to the third. So this way it's a little bit closer to the original way the function was written. But again, let me recommend that when you encounter any kind of function of this type, so a combination, sum, difference of functions that are power functions, or kind of power functions not completely obvious at the first sight, rewrite the whole expression as a combination of power functions in this form. And that makes it very easy then to apply the power rule individually to each term here. So the next function is also a combination of power functions. It's section 3.1, number 29. And here we have h of theta. So this is the Greek letter theta. I don't know why they do this. I guess they just want to throw you off pace a bit. I don't know. It's well, if you feel uncomfortable with the letter theta, you can just replace it by x if you want. Well, we'll do it with theta. It's just another letter, right? It's just, and I guess in mathematics, if they at some point they ran out of Latin letters and just then then we need Greek letters or something. So it's just another letter, and we'll treat it as any variable letter as any other. Now to compute the derivative of this function, if you look at this now, you will probably notice, there is something not that might be a problem, right? Because we take a product of theta with a function that is a combination of power functions with theta, right? So, but we haven't really learned how to take derivatives of products yet. We will do that in the next lesson. So if we waited to the next lesson, we could just apply the product rule here, which will be a rule that we'll learn in lesson 6. However, we can still differentiate this today using the rules that we have if we realize that we can turn this into a combination of power functions of the form that we know how to differentiate by just multiplying out here, right? So let's do this. So if we multiply out this expression, theta times theta to the minus 1/2 minus theta to the minus 2, we get theta to the 1/2 minus theta to the minus 1, right? Because theta is the same as theta to the 1, right? So then we have 1 minus 1/2, it's 1/2, and then 1 minus 2 is minus 1 here. And this is a function we can easily differentiate now using the difference rule and the power rule, right? So we would get that d theta h is, well, now we just take the derivative of this function, right? And that would be 1/2 times theta to the 1/2 minus 1 minus, now we have to put a minus 1 in front, theta to the minus 1 minus 1. Again, as before, we can simplify the whole thing a little bit. So this would be 1/2 times theta to the minus 1/2 plus, so minus times minus is plus, theta to the minus 2. And as before, this is a perfectly good form. But if you want, you can rewrite this a little bit. So it would be 1/2 to the, so theta to the minus 1/2 is, right, 1 over theta to the 1/2, and theta to the 1/2 is square root of theta, so we could rewrite this as 1 over 2 square root theta plus 1 over theta squared. And you see here something interesting happens with the derivative of the square root, so it becomes 1 over 2 times square root, right? Because this is the derivative of this term here. Okay, and this is the derivative of this term here. So that stays like 1 over theta form, the exponent becomes higher, and you change the minus here to a plus. But overall, once you have done this, you multiplied out, right? You've turned it into a form that we know how to differentiate. Again, next week we learn the product rule, and then you could also calculate the derivative of this function using the product rule. And will be a good exercise to see if you use the product rule, then, for example, for this function, whether you get the same result. But the most important thing here is first bring the function into a form or an expression that you can immediately apply the power rule to in each individual term. Then apply the power rule carefully, write out all the steps, so write out the leading term that you get from the exponent with the sign. It's very frequent to commit sign errors when doing this, right? And then write out the exponent too, right? The new exponent by explicitly writing -1. Again, it often leads to errors if you skip a step there. So do this very carefully, and then just simplify. And that's it. That's the basic template for differentiating these kinds of functions. So, especially when you take the quiz, make sure you go over these steps carefully and individually. Next, I want to go over a problem that has to do with finding equations for tangent lines. So this is section 3.1, number 51. Find the equation for the tangent line to this function, 2x to the third minus 5x squared plus 3x minus 5 at x equals 1. So I've drawn this function on my computer. So this is the graph of the function in the region that we're interested, right? Because we're supposed to compute the equation for the tangent line at x equals 1. Right? Here's x equals 1. And I've tried to draw the tangent line here to the graph, this red line, at x equals 1. And we are supposed to find the equation for this line here. Right? So the equation for a line, we need two things. We need the slope, right? So the slope of this line, and we need the y-intercept. But the slope of the line is clear. That's given to us through the derivative, right? Because that's exactly what the derivative is. It's the slope of the tangent at this point. Okay, so that's the first thing we should do, is figure out the derivative at x equals 1. So here's the function f of x, and we can, using our knowledge now how to compute derivatives of polynomials, we can easily do this now. Right? That's the first step we need to compute. So we need f prime of 1. Right? That's what we want to know because that's the slope of the tangent. So let's compute the derivative of f of x overall first. So f prime of x using the rules we have so far. So this would be 2 times 3 x to the x squared minus 5 times 2x, right, plus 3. Right. Here again the constant term just vanishes. Okay, so let's simplify again. So this would be 6x squared minus 10x plus 3. And accordingly, we get f prime of 1 is 6 minus 10 plus 3, and that's equal to minus 1. And that is actually seems correct, right? Because if you go back to the graph on the previous page, you will see the slope seems to be more or less minus 1, and now we just confirmed it algebraically, right, by computing the derivative and plugging in 1 as a value. We get minus 1. So this is our slope. Right. It's the slope of the tangent line. So now we need the y-intercept. Right? How do we find the y-intercept? Right, so we want a function of the form y equals mx plus b. Right, so this is what we want. We have m now. We know m is minus 1, but we need to know b. Well, there's various ways you can describe the equation of a line and then transform one of those ways into each other. What we have is the slope, but we also have a point on the line. The point that we have is given by plugging in 1 into our function. Right? If we plug in 1 here, we get a point on the line. Namely, right? So we have f of 1, and you plug this in, so this would be 2 minus 5 plus 3 minus 5. Right, and so that would be minus 5. So we know the point 1 comma minus 5 is on the line, right? So we have now a point plus the slope, and we can transform this now into the usual form slope plus y-intercept. Here's the point slope form, right, of this. Y minus minus 5 equals slope times x minus 1. Here we have the point on the line 1 minus 5. And now we can just simply rearrange the terms here to get to our usual point slope y-intercept form. Namely, y would be equal to minus x plus 5 minus, bring it over to the other side, minus 1. This would be plus 1 minus 5 would be minus 4. So this is our equation for the tangent line. Okay. So let's go over the steps here, because this is the general template that applies to all of these kinds of problems where you have to compute the equation of the tangent line. First, you compute the derivative. You plug in the x value at which you want to compute the equation of the tangent line. In our case, that's 1. That gives you the slope of the line. Then you compute the original function, add the x for which you want to compute the tangent line. That gives you the point on the line, right? Then 1 comma f of 1 gives you a point on the line, and that you can use then to put into this point slope form and transform it into the slope y-intercept form, right? Mx plus b. That's the 4 essential steps, and that's the template that you can use for all of these types of problems. Next, I want to discuss the derivatives of exponential functions. And I guess next to the derivative of constant functions, which are very nice because they vanish, the derivative of the exponential function e to the x is the next nicest derivative because it's the same, right? It doesn't change. So in other words, the derivative d dx of e to the x is just e to the x. Now that's really nice, right? So there's just, it stays the same, which is pretty amazing, right? Because I already kind of told you that e occurs in so many ways in mathematics and has so many nice properties and fascinating properties. So here's one, right? So when we encountered e for the first time, it came as kind of describing growth processes, right, related to, for instance, continuous accumulation of capital and interest and so on. Now it appears as how in the world might this be related to the property that its derivative stays the same? Of course, you can explain this all. Unfortunately, we'd have to go a lot deeper into the definition of E and so on to fully understand this. We will do a little bit about it in the next lesson. But if you're interested, let me know and I'll give you a few pointers to where you can learn more about these fascinating properties of E. Anyway, so that's the most fundamental rule about the exponential function. So the derivative of e to the x is e to the x. Very nice. But it is important to keep in mind that this, right, very simple relation is only true for the base e here. If the base is a, so any other number instead, this identity becomes not quite as nice, but still pretty nice. The derivative of a to the x is ln a times a to the x. So we just have to multiply now by the logarithm of the base. And of course, if you plugged in e here for a, then this would be ln of e, which is 1, so it would just be multiplying by 1. And that's the same as up here, right? So not quite as nice. If you have other bases, you do not forget to put the logarithm of the base in front, right, as a multiplicative term. Why this is so, well, we can see this next week once we have the product rule, the chain rule, right? Because the chain rule tells us how to differentiate functions which are compositions of functions. And actually we can write this function here, a to the x, we can write as e to the ln a times x, right? And once you apply the chain rule to this expression here, you will see that you get exactly this out, because you have this inner function, so to say, ln a times x. So that's the reason behind this, why you get this term out here. And finally, this right, a to the x, and what we see here, right, that we get an ln a in front because we rewrite it as e to the ln a ln of a times x. This also tells us that the derivative of d of a function of the form e times k, e to the k times t will be simply k times e to the kt, right? So here, this is a special form of this rule, right? Of this rule here, because here we have a to the x would be e to the ln of a times x. So k in this case would be just ln of a, right? And in the derivative, this comes out as ln of a. Here we have e to the k times t. For the derivative, we just keep the original function and just add this multiplicative constant k right in front. So this is pretty much all you need to know about differentiating exponential functions. All right. So the basic rule, very nice. If there's a slight deviation in terms of the base from e, remember to add this logarithm of the base as a constant. Or in general, if you don't have e to the x, but e to the k times x or k times t, remember to put in this multiplicative constant, this k here, as a multiplicative constant in the derivative. Now, equipped with this new rule, we can apply it to these kind of functions we've looked at before, right? Remember, we looked at combinations of power functions, sums of power functions. Now we can also look at combinations, sums of power functions here with exponential functions, right? And by the sum rule, the derivative of this is just taking the derivatives of the individual terms and summing them up. Okay, so let's just do this. So d over dx of y is derivative of this, so d dx 2 to the x plus d dx 2 over x to the third. Let's do the same thing we did before. Let's rewrite this in the nice form, or in the appropriate form. So here we have 2 to the x, but here in the second term we have, so this would be 2 times x to the minus third, right? And now we just apply the power rule or the exponential rule. So in the first case, this would be ln of 2 to the x. Now the second term would be minus 2 times minus 3, because it's a power function, right, times x to the minus 3 minus 1, right? And hence we would get ln of 2 times 2 to the x minus 6 times x to the minus 4. So this is the right. And again, now you can, this is the standard template for all these kinds of functions. Right now, the only difference from before is that we have a mixture now of exponential function and power function. But again, we use the sum rule to first apply the derivative individually to each function. And then here in the case of the power function, we rewrite it in a form so we can nicely apply the power rule, right? And then here we apply the exponential rule. The only difference now is you first have to determine which one is an exponential function, which one is a power function. But that should not be too difficult, because in exponential function the variable is in the exponent. In the power function the variable is in the base. Of course, now if you might be asking, what about a function like x to the x? How do we differentiate that? Is that an exponential function or a power function? Well, we'll come to that at some point. So, but just if you're curious, you might want to think about this a little bit. But for now, we're fine. We'll only look at functions of this type. Next, we have the derivative of the logarithm. And that's also very fascinating because we've seen so far that somehow there seems to be power functions, there seem to be exponential functions, and somehow they stay within their type, right, when we differentiate them. So for instance, if we differentiate a polynomial, we get a polynomial. We differentiate a power function, we get a power function. Right? If we differentiate the exponential function, we get an exponential function. But now, if we differentiate the logarithm, right, so the natural logarithm d dx of ln x, that's 1 over x, which is, strictly speaking, a power function, right? It's x to the minus 1. Very, very fascinating, right? So where does this connection come from? We will see a little bit when we talk more about the theory of how these rules are justified in the next lesson, so in lesson 6. But for now, I just hope I arouse your curiosity a little bit. So why is that? There's an interesting transition, right, happening from something that is more living in the realm of an exponential function, right, because it's the inverse of the exponential function, and then leading to a power, very special power, kind of power function. Anyway, the rule is simple enough, right, so that you should have no problems of memorizing it, right? Derivative of the natural logarithm is just 1 over x. In the quiz, you're asked to compute derivatives of functions that are kind of compositions of logarithm and another function, like in this example here, logarithm and x of x to the third. We haven't learned the chain rule yet, right? And so strictly speaking, you would think, oh, how can I take the derivative? Because I only know the derivative of ln x and so on, right? The nice thing here is that the logarithm has these nice rules, algebraic rules, about the terms, how the logarithm kind of interacts with other algebraic operations, such as sums or products and so on. So the trick there is to rewrite the whole thing as using the laws of the logarithm. So this is the same as the derivative of dx of 3 times ln x to the third, just x, of course, right? 3 times ln x, that's the law of the logarithm. But now we see here we have a function of the form constant multiple times ln x. So we can just apply the constant rule. It's just a constant rule of a function whose derivative we know. Right? So we just apply the constant multiple rule and we get that's equal to 3 times. So just carry the constant, take the derivative of the remaining function, which we just learned is 1 over x. So 3 over x. So this is a nice thing about applying the law of the logarithms here. And when you take the quiz, keep this trick in mind. Of course, next week we learn the chain rule, and then you could also differentiate this function using the chain rule. And again, there's a nice test to see that and you understood everything, that you get the same result. The last rules for this lesson concerns sine and cosine. And just as the exponential function offered something really truly surprising and amazing, that namely that the exponential function is its e to the x is its own derivative, something similar happens between sine and cosine. So there, here the basic rule is that dx of sine x is cosine x, and dx of cosine x is minus sine x. this seems indeed a little bit surprising, right? So why, again, do we have functions that are so intimately related? Not only is cosine just a shift of the sine function by pi over 2, right, along the x-axis, and vice versa, but why would their derivatives also be related in this close way here, the close fashion that the derivative of sine is cosine. So not only is cosine just a shift of the sine function, it is also its derivative. Very, very surprising, very amazing. It turns out that ultimately the reason is more or less the same as why the derivative of the exponential function is itself. So sine and cosine are intimately related to e to the x, to the function e to the x. And you could there's also a way you can explain this geometrically, which I don't want to go into here. But so this is the fundamental rule you need to learn. And there's a few variations of this rule that you will also need, but this is the basic thing, right? So this is the basic relation, and you can do most of the problems you'll encounter keeping this in mind, right? So if you differentiate sine, you get cosine. If you differentiate cosine, you get minus sine, right? And then, of course, if you differentiate minus sine now by the constant multiple rule, you get minus cosine. And then if you differentiate minus cosine, so let me write this. So d dx minus sine, you get minus cosine by the constant multiple rule. And now if we differentiate d dx minus cosine, right, that would be minus derivative of cosine would be minus sine, which is just sine. So after 4 derivatives, right, after 4 derivatives starting, right, so starting after 4 steps, you're back at sine again, right? So first derivative is cosine, second derivative of sine is minus sine, right? Third derivative is minus cosine, fourth derivative is the function itself again. Amazing. And then it starts all over. So there's a lot of interesting stuff going on with these functions. I'll leave it, for today I'll leave it at this. And we'll come back to that when we do the chain rule and everything. But just for now, keep in mind e to the x and the sine and cosine function have something very special going on with respect to their derivatives. And we'll learn more about that next week when we look at the chain rule and look a little bit deeper into the theory of why these rules are what they are. I hope for now this lecture has helped you a little bit understanding the material a little bit better, and prepares you to take on the quiz and so on. As always, if you have questions, email me or post on Piazza. You know the deal, hopefully, by now. Okay.